Something strange is happening on the surface of Betelgeuse, Orion's crimson supergiant on its deathbed. The star made headlines in December 2019 when it suddenly began to decline, reaching an all-time low in brightness by February 2020, a phenomena later termed the Great Dimming of Betelgeuse. Although it returned to its normal brightness later that year, it piqued astronomers' interest, causing them to point some of their most powerful telescopes at it for a closer look. They discovered something astonishing. The surface of the star is boiling, producing a cosmic illusion. Betelgeuse is a huge deal. It is one of the most captivating stars in the night sky. It was born in a star nebula and spent 90% of its life in the main sequence phase, converting hydrogen to helium in its core. However, because Betelgeuse has a mass nearly 15 times that of the Sun, it evolved in a different way. Instead of becoming a red giant, like most Sun-like stars, it evolved into a red supergiant. Betelgeuse has piqued astronomers' interest because it is uncommon to see a star in its last stages of life with naked eyes. This makes it an excellent laboratory for studying the processes that lead up to one of the most cataclysmic star explosions, a supernova. The last significant supernova seen in the Milky Way was Kepler's supernova in 1604. Since then, no further supernovas have been seen in our galaxy within the naked eye limit. So naturally, whatever happens to Betelgeuse is a major problem. Even as Betelgeuse's brilliance decreased, astronomers hypothesized that this could be a sign of an approaching supernova explosion. To learn more, they utilized the Atacama Large Millimeter Array, or ALMA, to closely watch the supergiant. ALMA observations found that the dying star appears to be spinning fast, with rates that exceed those expected by existing physical principles. This was puzzling. Why does Betelgeuse appear to be spinning faster than other stars of its age? Is this apparent rapid rotation an indication of an approaching supernova? A supernova, such as Betelgeuse, causes a cascade of cosmic processes. The ALMA surface radial velocity map of Betelgeuse provided the first indication that anything strange was happening. A surface radial velocity map is a visual representation of the rate at which various components of an object, such as a star or planet, move toward or away from an observer. It employs colors to indicate the speed and direction of movement across the object's surface. ALMA studies indicated that one half of the star's visible hemisphere was blue-shifted, indicating it was approaching us, and the other half was red-shifted, indicating it was traveling away. These data were critical in precisely determining the star's rotational velocity. When these results were compared to Hubble Space Telescope views, it was determined that Betelgeuse was rotating rapidly. According to some ideas, Betelgeuse's unusually high rotation rate may be explained by its previous role in a binary system, where it consumed a lower-mass companion star, a process known as celestial cannibalism. While this is not unusual for red supergiants, there is no clear proof in Betelgeuse's instance. However, if Betelgeuse formed as a single star, its rapid rotation deviates unexpectedly from predictions. To understand why Betelgeuse's quick rotation is problematic, we must first consider the star's sheer immensity. Betelgeuse is 15 times more massive and 1,000 times larger in diameter than the Sun. If it were in place of the Sun, it would envelop the Earth and reach Jupiter's orbit. Furthermore, Betelgeuse is no longer a main sequence star like the Sun, but has developed into a red supergiant. Betelgeuse and other stars grow in size as they age and cool. According to the concept of angular momentum conservation, this expansion should slow their rotation. Furthermore, they lose mass through stellar winds, which leads to a decrease in their rotational velocity. According to current hypotheses, red giants should rotate at speeds of roughly 1 km per second, and red supergiants, such as Betelgeuse, at even slower speeds of less than 0.1 km per second. Betelgeuse, on the other hand, defies these assumptions by revolving at approximately 5 km per second, which is 50 times faster than the average rotation rate for stars in its category. To answer the mystery of Betelgeuse's extremely high rotation speed, astronomers had to determine whether the measured rotation was real or a measurement error. They investigated how various actions on the star's surface could be misinterpreted as rotating movement. To explore deeper into this issue, scientists used the ALMA telescope, which has 66 separate antennas of varying diameters and is one of the most advanced radio telescopes in use today. Astronomers investigated the heated gas in Betelgeuse's outer atmosphere using ALMA's capacity to view light at submillimeter wavelengths. The researchers wanted to know if Betelgeuse's rapid rotation was mistaken for anything else on its surface. They hypothesized that what's going on is a mechanism known as convective flow, which is how stars like Betelgeuse transport heat around. Convection causes hot material to rise to the star's surface because it is lighter, while colder, heavier material sinks. This forms large whirling patterns known as convective cells, which resemble huge boiling bubbles. These patterns can extend from the star's outer layer to its core. The team hypothesized that these boiling bubbles were creating an illusion of rotation, with one group of bubbles rising on one side of the surface and another sinking on the opposite side, giving the appearance that the star was spinning by causing some parts to come towards us while others moved away. This migration may explain the blue-shifted and red-shifted regions shown in ALMA's maps. To test their hypothesis, the researchers developed a computer model of a non-spinning red supergiant star with a boiling surface similar to Betelgeuse. They compared the model's behavior to observations from the ALMA telescope. Surprisingly, the simulated star and the actual observations matched perfectly. This validated their notion that Betelgeuse's surface is bubbling up like a pot of boiling water rather than whirling rapidly. This bubbling effect is so strong that even the most advanced telescopes cannot distinguish between it and the star whirling. The discovery gives additional proof of Betelgeuse's unexpected behavior, which is not a new occurrence for astronomers. In the past, Betelgeuse has been the center of unexpected events. For example, the Great Dimming Occurrence, which occurred nearly 4 years ago, was finally explained by the notion that the star released a massive volume of hot gas. As the gas cooled outside the star, it created dust which momentarily covered some of the supergiant's light, making it appear fainter from Earth. In 2023, Betelgeuse had another unusual behavior. Its brightness increased by around 50%. Initially, astronomers suspected this was a forerunner to a supernova explosion. However, subsequent investigation found that this was a residual impact of the 2020 Great Dimming. The huge outpouring of dust and gas during the event disturbed Betelgeuse's normal brightness cycles, which typically last 400 days, 185 days, 230 days, or even up to 2,100 days. The Great Dimming disrupted the 400-day cycle, shortening it to 200 days and resulting in an unanticipated increase in brightness. Predicting when Betelgeuse will go supernova is tricky because the star's exact stage in the lifespan is unknown. Scientists need to know whether Betelgeuse is in the helium or carbon-burning phase. This has a significant impact on when the supernova will occur. At 550 light-years, humans have an excellent vantage position to observe this cosmic extravaganza. When a supernova does occur, the first sign will most likely be a surge in neutrinos, small particles produced in large quantities after a supernova explosion. The Supernova Early Warning System, or SNEWS, searches for these early warning indications using a network of neutrino detectors. Following the neutrino burst, a supernova would emit an enormous amount of energy, becoming so brilliant that it might be seen during the day for 2 to 3 months before gradually dimming. Although a Betelgeuse supernova would be a stunning spectacle and pose no threat due to its distance, it would cause a notable alteration in our night sky. Betelgeuse is one of the shoulders in the constellation of Orion, and its disappearance would make Orion appear missing a shoulder with the remnants of the explosion invisible to the naked eye. Many people wonder if we can study Betelgeuse with the James Webb Space Telescope and accurately anticipate its supernova? So the answer is no. Webb, despite being highly strong, is unsuitable for monitoring it. It is intended to examine distant and weak celestial objects. However, Betelgeuse is around 1,500 times brighter than the sensitive detectors of JWST, so we can't use it to accurately anticipate the star's evolutionary stage. If you learned something new from this video, please like and subscribe to our channel.